very much. Okay. Right. Okay. So, all right. Um, all right. Yeah, this works. Okay. So, yeah, I want to say right away that it's my pleasure to give a talk about my research at my alma mater. I want to thank Professor Stefan Karaben for the invite, and of course everybody in the team for organizing this seminar. I think it's quite fantastic seminar. I studied at Jacobs University from 2011 to 2014, BSc Physics. And like Professor Stefan said, I went to Switzerland to complete my higher education. And today I'll tell you about the research work I conducted at ETH Zurich to complete my doctoral thesis. So in my doctorate, I developed novel approaches to treat or include nuclear quantum effects, right, such as tunneling and delocalization in chemical reaction rates, right? And in particular, I looked at path integral based approaches, right, to do so. And I developed a number of path integral based approach to compute chemical reaction rates for a variety of reaction. And today I will speak about a particular kind of reaction, which is electron transfer reaction, right? So I want to compute rates of electron transfer reaction for systems in condensed phases, right? For liquid systems, right? So to begin, simply what are chemical reactions? The chemical reaction typically consists of reactants and product. So the reactants, they react together, right, to form products. And an important question to ask is how fast, right, are these products formed? What is the rate of reaction? It is important because we want to know if the products form super slow, such that it never forms, or it forms explosively fast, right? And this rate really depends on, for example, if it is a thermally activated reaction, it depends on temperature. It also depends on height and width of the energy barrier. So it has to overcome this barrier to form products, right? So it overcomes barrier, for example, as a result of thermal fluctuation, right? You supply heat and then it reaches a certain state and then it reacts. So classically, reactants, they have to overcome this barrier, right, to react. So the chemical species, they have to reach at this transition state, which is this quasi-equilibrium state. And then at that point, we consider that a reaction has occurred, right? But quantum mechanically, it can tunnel, right? So tunneling is a quantum phenomena, and tunneling enhances chemical reaction rates. And if you don't include tunneling in your rate calculation, one is going to massively underestimate reaction rates. In our bachelor's, I guess we were quite fond of looking at this barrier penetration problem for rectangle barrier, and we computed, for example, we computed like probability current, and from that we would compute reflection and transmission probability densities, right? And from that you can essentially compute tunneling rate. But here on the plot, you see it's not a rectangular barrier. It's the so-called Eckhart barrier, and it is more realistic, right, for chemical reactions, for chemical systems. And as you can see, so this is a quantum particle, right? This fuzziness and this quantum particle comes from the left, and part of it is reflected and part of it is transmitted, right? And it is this transmitted component that characterizes the rate of reaction. So one solves the Schrodinger equation to obtain the time dynamics of quantum system, and the solution of Schrodinger equation is going to give you the rate of quantum tunneling, right? So I have made a simple video a movie to illustrate what quantum tunneling looks like. So you see, I've initialized a particle as a Gaussian function on the left of this Eckhart barrier, and now I'm going to propagate it, right? So it's going to move to the right of the barrier. It is going to hit the barrier, and part of it goes inside the barrier, and part of it is reflected, right? And this is typical of quantum tunneling, right? And so with this transmission reflection coefficient, you can obtain your chemical reaction rate, right? How much entered through the barrier. So for this, to produce this movie, I used this numerical approach called split step Fourier approach, and from this one could obtain a time dynamics of this Gaussian function. But solving Schrodinger equation is exponentially difficult on classical devices. I say classical devices just to make distinction, because there is also now quantum devices, although they're still small. But on our classical devices, this is exponentially hard problem, and it's because with increasing dimensionality, the size of Hilbert's space grows exponentially, right? And diagonalizing the system Hamiltonian in this exponentially large Hilbert space is difficult. So one looks for a better approach that scales favorably with dimensionality. And now enter semi-classical approach. So that is an approach which is seen to scale favorably with dimensionality, and especially in computing rate of chemical reactions. And this is one of the subtopic, I say, of this presentation. So now one of the popular semi-classical approaches is instanton theory, and I'll talk more about instanton theory in the later slides. But let me tell you that tunneling event is typically characterized by imaginary time, right? So why is this so? It is because tunneling happens under the barrier, and under the barrier, the momentum of the particle is essentially imaginary, right? So you can think of momentum. Of course, momentum is m dx dt. So either you can make position imaginary or time imaginary, right? And that will give you momentum imaginary. But physicists chose to make time imaginary, and hence the concept of imaginary time came into being. So the dominant tunneling path is called an instanton, and in simple words, instanton is defined as a periodic orbit in imaginary time. This nomenclature, I guess, was first, I looked through the literature, and I guess it was first given by Dutch physicist Gerard 't Hooft. And it was popularized by Sidney Coleman, right? The picture you see on the right. I'm not too much into quantum field theory, but it looks like he was looking at barrier penetration problems in quantum field theory. And in his notes, the uses of instanton. So this is how he essentially explains the instanton, right? So the energy barrier on the left is the barrier that you see in the previous slide, right? So it has this maximum, and the reactant starts on the left, and it hits the barrier and then moves to the right, right? And that's when the reaction occurred. So now let us invert this potential, right? So you invert this potential, and you make it look like the one on the right, and you obtain something like this on the right, right? Now let's imagine you roll a ball from left to right. So it traces this path, right? So now if you roll this ball, it traces this path. Now you invert this back, right? And this path that is traced by this ball in this inverted potential, and you invert this back again, then that will give you instanton, right? So this is the path that the ball traces. So you have these are like minus a is here, and you have plus a, and in time, right? It is initially here, and it moves faster, and then slower, and then it comes here, right? So basically, an instanton is basically classical trajectory of a quantum particle in imaginary time, right? So you can see here, it's a classical trajectory in inverted potential, which is like this. You invert it back, and you locate this instanton, right? So that is how one locates an instanton. And so there are like, so basically it is equivalent to propagating quantum particle in imaginary time. And why is this so? So you see there are like different kinds of action. So this is Minkowski action, right? And this is Euclidean action. So the quantum propagator has this e to the power I s action by h bar, right? And now let us suppose you switch t to become minus I tau, right? I've written beta h bar here. Let's say you replace this minus I tau here and here, and you essentially get this plus, right, in front. And now your this quantum uh, propagator is going to become it starts to look like quantum Boltzmann operator, right? So EIS is going to go to E minus S, and now S is going to be a Euclidean action, right? So you see, when it comes to tunneling, right? In physics, especially, for example, quantum dynamics, right, where coherences are preserved, things oscillate. But in chemistry, for example, when we look at tunneling in a condensed phase reaction, things decay, right? Because we're looking at Euclidean action, and now there is no this phase term, and one can compute chemical reaction rates, right? Out of this using this imaginary time path integrals. And it is very useful to obtain a discretized version of this Euclidean action, because, for instance, the computing action, right, for complex molecular system is difficult analytically, and we discretize using a number of so-called ring polymer beads, right? So you use finite differences for derivative and trapezium rule for integral, and you can obtain your action in this discretized form. So it contains this spring term, which comes from discretization, right, of this guy here, and then there's this potential energy term right here. So what it looks like many copies of classical particle connected by harmonic springs, right? So essentially, that is what delocalization is. You have a single particle, which is a classical particle, and you make many copies of it, right? And each of these copies are connected by harmonic springs, and you essentially get a delocalized structure such as instanton. And this is the instanton trajectory, which I optimized for two-dimensional potential energy surface. So this is minima, right? This is where the reactant side. This is the product side, and these are two different instantons that I have optimized for this Muller Brown PES. And there are two different instantons because these are instantons at two different temperatures. So these are at lower temperature. This is at lower temperature, and this is at higher temperature. So if you increase the temperature, the instanton becomes smaller and smaller, and ultimately, in the classical limit, it collapses at the transition state, right? So in the classical limit or at really high temperature, you don't need a delocalized structure because there is no prominently seen quantum effects there, right? So I guess yes. So I mean, there's also some useful thing about using path integral approach because there is this natural way to see classical limit, right? With imaginary time path integrals, one can obtain a number of equilibrium averages, right? So partition function is one of them, right? It's easy to obtain equilibrium averages such as the partition function. And the partition function is, of course, defined as sum over all the microstates, as you can see here, right? Here, beta is the inverse temperature, and which is defined as 1 by kBT. So to obtain this partition function, one essentially solves Schrodinger equation, right? And for the solution of Schrodinger equation gives you this eigenenergies, and you sum over all this Boltzmann factor essentially, right? But for a complex system, as I said, this is difficult, right? Solving Schrodinger equation is difficult. So one is to find a better approach that has good scaling with system size. And one can write it as a trace of quantum Boltzmann operator here and use path integrals evaluate this quantity efficiently using Monte Carlo approach, right? And you see this integral is dominated, right, for partition function, and we are talking about reactant partition function, and this is the reactant, right? So reactant is the one on the left, well, the minimum energy configuration on the left. So this is for a harmonic system. For Eckhart barrier, reactant was here, which is not bounded, right? And one is to use this bounds for some length to compute the partition function, but for a harmonic system, it's bounded, right? So it's the well on the left is the reactant well, and this is difficult to compute because one is to solve Schrodinger equation, right? And with imaginary time path integrals, you can obtain a partition function, because one can essentially write one can essentially trace our Boltzmann operator in this manner. And you see, for a partition function, this integral is dominated by minima, right, at the bottom of the well. And so the instanton is first order saddle point on a multidimensional PES, whereas the reactant partition function, the integrand of reactant partition function, is dominated by minima of this multidimensional function, Euclidean action, right? And basically, in path integral representation, this is what it looks like, right? And I guess it'll be easier to let me just the time. I guess it is easier to illustrate how to compute, right, partition function using path integrals with a harmonic system. Let's do a simple illustration, right, with harmonic potential. For a harmonic system, the Hamiltonian is at most quadratic in position of this ring polymer beads. So we can also call it ring polymer beads or path integral beads. And as I told you, they are like connected by harmonic springs. And furthermore, it is moving in some potential energy surface, right? It's moving. And since the Hamiltonian is at most quadratic in position, one can use normal mode transformation to diagonalize this, right? Hamiltonian, right? And the first mode, the first normal mode is the centroid of this ring polymer. And there are other modes. There are swelling modes, right? For example, that accounts for delocalization. And there are higher order modes which becomes less and less important if the system is not so inharmonic, right? And so one can quantify, well, one can look at a number of quantities, right? Different features of this ring polymer, path integral beads connected by harmonic springs. And one can compute, I found this in the literature, and it's easy to see. So this is radius of gyration of this ring polymer. And you see here, if the temperature is large, the radius of gyration is going to become small. So with increasing temperature, the ring polymer is going to delocalize less. So that is classical limit, right? Which is natural, I guess. And for large mass, for example, right, where quantum effects are not so prominent, you see again this radius of gyration becomes smaller. And but for larger h, Planck's constant, which is more quantum, it swells, right? So this particle shows more delocalization, right? And so these are the normal modes of the ring polymer for harmonic system, right? And these modes, these are this is the centroid, and these are other higher order modes that analyze the ring polymer Hamiltonian. And it with this eigenbasis, one can essentially decouple this harmonics, this particles, and you can write it as an independent oscillator, right? As you can see here. And right, so you can write it as independent oscillator, and now this becomes a Gaussian integral, right? And it becomes Gaussian integral, and using this simple formula, there is a formula to go from here to here, you obtain the partition function, right? So it's quite efficient to use path integrals to obtain partition function in this way. Right. Okay, so far we have looked at instanton, which is the first order saddle point of your ring polymer Hamiltonian. And we have looked at a minimum action path, right, which basically dominates the reactant partition function. So how do you define rates, right? How can you compute rates given instanton and given minimal action path in the reactant well? So this is the formula. It looks a little bit complicated, but this is the exact formula to obtain rates of chemical reaction. And chemical reaction rate K is defined as the ratio of partition function at the transition state, right, at the top of the barrier, and the reactant partition function, right? So if you do the ratio, it's going to give you rate K. So this quantity here, this one, it involves integral over x position and t, right? And this integral is dominated by something that looks like instanton, right? So it's dominated by first order saddle point of your Euclidean action. The path looks like this. This moved a bit. This yellow dot should be here. That is going to be the reactant well. And this ZR, which is the reactant partition function, is dominated by the configuration of your ring polymers at the minima, right? And if you do the ratio of these two, it's going to give you a rate of chemical reaction. And in my PhD thesis, I looked at computing the rate of chemical reaction for both adiabatic reaction and non-adiabatic reaction. So what does adiabatic reaction mean? So adiabatic reaction is the one which involves just one potential energy surface, right? So you look at systems in ground state and it stays in ground state or just one electronic state. And in non-adiabatic reaction, you need to introduce multiple electronic states, and each of these multiple electronic states has associated potential energy surface, right? So this is one surface reaction, adiabatic reaction. This is two surface reaction, non-adiabatic reaction. This green corresponds to electronic state 0, and red surface corresponds to electronic state 1. And there is also barrier, right, for non-adiabatic reaction. And the only difference between adiabatic reaction, non-adiabatic reaction in terms of how you formulate your rate constant is in this flux operator. For adiabatic reaction, the flux operator is defined like this. So it's a delta constraint which spins one of the coordinate of your ring polymer to some intelligently chosen location in your potential surface, and it has this momentum operator, right? So it measures your flux at some position, right? For non-adiabatic reaction, it is defined in terms of this position operators. Sorry, electronic state operators, projection operators, I meant. And like I said, it involves two electronic states, 0, 1, and so each of the electronic states has associated potential energy surface. One has its own associated potential energy surface, right? And the Hamiltonian can be written like this. So it is basically a tensor product of electronic state and nuclear Hamiltonian. So in non-adiabatic reaction, especially in the golden rule regime, this electronic states and nuclear states that are coupled, right? And you cannot treat them separately. So and it is more of a challenge to compute rates of non-adiabatic reaction than adiabatic reaction. And in this talk in particular, I will talk about non-adiabatic reaction, this sort of Hamiltonian, and how to compute chemical reaction rates, right, for those kind of systems. I guess with this slide, I want to make clearer what exactly is non-adiabatic reaction in terms of physical picture, right? So electron transfer reaction is one of the most fundamental chemical reaction. For example, electron transfer reaction, you could think of iron in +2 and +3 oxidation states, and electron jumps right from +2 to +3 oxidation states as a result of thermal fluctuation. And in the course of this jump, the solvent nuclei right around this chemical species, this ferric pairs, these are water molecules, they rearrange their polarization, right? And at low enough temperature, they rearrange their polarization via tunneling, right? So the tunnel, when electron jumps, the charges redistribute and their polarization moves. And this movement, classically, at low temperature, it is slow, right? But if you include quantum effects, there's delocalization going. So it moves as a result of tunneling, right? And in my PhD thesis, I quantified the rate of quantum tunneling, nuclear quantum tunneling in processes like this. So this electron transfer reaction, it considers involvement of at least two weakly coupled electronic states, since we're in the golden rule regime. And there's a very famous approach called Marcus approach, or Marcus theory, and Rudolf Marcus, he won a Nobel Prize to develop a theoretical framework for electron transfer reaction. It's very accurate to treat systems at high temperature, but at low temperature, it fails because it doesn't include nuclear quantum effects, right? And in my PhD thesis, I devised technique to include nuclear quantum effects in electron transfer reaction, especially for condensed phase electron transfer reactions, right? And that's what I'm going to show you. Sorry, just so that I'm on time. Okay, so now the first approach I want to talk about instanton theory, because and this is a semi-classical approach, as I told you, because my approach is related to instanton theory. I think I should briefly tell you what it exactly is. So the instanton theory is one of the most successful rate theories for non-adiabatic reaction. As I told you, there are two electronic states, V0, 0, and 1, and each of these electronic state has associated potential energy surface, right? So you see two electronic states, and depending on your reactant or product electronic, depending on if the electron jumped or not, you get this potential energy surfaces, and each of these have their minima, right? And now this potential energy surfaces, they intersect at this diabatic crossing, and again you get something like a barrier, right? Just like in adiabatic reaction, this Eckhart barrier or your rectangular barrier, you get a barrier also in this non-adiabatic reaction. And one can locate an instanton on this barrier, essentially by obtaining a first order saddle point of your Euclidean action. An instanton looks something like this. So it starts at diabatic hop, and it moves first in potential energy surface V0, bounces, right? Here where energy equals to where its energy equals to V0, E equals V0, and again comes back and hops to another electronic state, bounces in this red surface, which is the second potential energy surface, and joins smoothly at this diabatic hop again, right? So that is instanton. And instanton approach makes harmonic approximation for quantum fluctuation, right? So it treats quantum fluctuations harmonically, and the whole formula at the end becomes very simple, right? So it just includes a P factor, which accounts for second variation of action, and it has this E minus S H bar, and S is evaluated along instanton trajectory, right? And it's very simple to implement, and it's very successful. And I guess I can illustrate this better with this example. So these are the plots of Euclidean action on the left and exponents of negative Euclidean action on the right, right? So if your Euclidean action varies like this along position, the exponent of that is going to have a peak at this important point, and this important point is the one that optimizes, extremizes your action, right? So that is the instanton configuration. And what instanton theory does is makes a Gaussian approximation to your function that looks like that, because essentially you can write that exact formula in terms of path integral notation that looks something like that, and you treat you expand S Taylor series around x tilde, and this becomes basically Gaussian integral of your position, right? And this is how you obtain instanton theory, right? But an important downside is that you see if this function is not approximately Gaussian, which is the case when the system is very anharmonic, right? Or when you have multiple saddle points. We call multiple saddle points, meaning there are multiple ways a reaction can occur. It can have non-adiabatic channels on the right, on the left, right? And for systems with multiple ways to react, or with multiple instantons, you will have something like two of these curves and the overlap, and this whole thing will look sort of oscillatory. And for those systems, instanton theory is not good. And my PhD thesis, I developed approach that goes beyond instanton theory. We call it golden rule quantum transition state theory, GRQTST. And so now to explain about GRQTST, so think of like propagating in imaginary time from position space A to B. So this red path is the classical path with extremizes your action, right? This is what classical mechanics uses to compute the rate. And there is this other path in the vicinity, right, in the neighborhood that still extremizes your action, right? And these are like harmonic quantum fluctuations, right, which instanton approach includes. But I want to go beyond harmonic quantum fluctuations and include anharmonic quantum fluctuations, higher order paths, right? And this is exactly what I did in my PhD thesis. So you see, instead of just evaluating this at like particular configuration, there's an integral, right? And allows for sampling of dominant tunneling paths as well as other paths in the vicinity of this dominant tunneling path. And like I said, and as I said, dominant tunneling path is the instanton path, right? And it goes beyond instanton approach. And a good thing is that it is derived, it's motivated by fundamental principles, right? For example, energy conservation. So it samples all energy conserving path to go from A to B, for example, right? Reacting to product. And it has this kind of funny thing here, delta constraint. And this delta constraint is basically sigma. It's a functional of paths. Now the question is, what is the sigma, right? How can you obtain sigma such that this whole thing samples instanton-like path and gives you the correct answer for rays, right? And we tested sigma using different functions, right? Physically motivated. And for example, we at the end concluded that sigma, if it is derived or if it is based on virial energies, is going to give you the correct answer, right? So sigma is basically 2/3 beta virial energy of the reactant path minus virial energy of the product path, right? 0 and 1, 0 is reactant, 1 is product. And virial energy is defined like that. So that is Lagrangian and can be 0 or 1. And that is generalized coordinate. And we chose our generalized coordinates such that at the boundaries, so this was derived by taking partial integration, by performing partial integration on thermodynamic energy. And after taking partial integration, the thermodynamic energy gives this boundary term. And if you choose Q, which is the generalized coordinate, intelligently, you can throw this more complicated boundary term. And you're left with this very simple expression, which depends on the gradient of potential times x position plus v, right? And it was important to throw that boundary term so as to avoid sampling of non-instanton-like paths, right? And just to illustrate here, this is a ring polymer, and green correspond to paths on the reactant side and red on the product side. And here I show you results of using a virial constraint. Sorry, this one. And what happens if you don't include this delta constraint, right? If you don't include the delta constraint, it's going to sample not the region that you want. We want our integrand to sample region near here, which is the transition state, right? It should first be there and then the reaction happens. But if you don't include constraint, it's not going to sample the correct configuration space. But if you include virial constraint, it's going to sample instanton-like path for range of imaginary time split. And imaginary time split here simply means the distribution of beats on the reactant and product sides, right? So for range of imaginary time split, you still obtain instanton-like paths, right? So this was, and we found that this works well for a lot of systems, and I will show you some results. We tested our approach on system bath model. So on the x-axis, you see thermodynamic driving force. On the y-axis, you have quantum rate constant, right? And thermodynamic driving force basically tells you if you know how much driving force you have, right? Like you see here, if you make this lower and lower and lower, thermodynamic driving force is higher there. And if you make it really, really low, you reach at this point called inverted regime. And this is a funny point because at this regime, the rate starts to decrease again. You lower this rate potential. Sorry, I don't know. It's you lower this rate potential, it's going to increase the thermodynamic driving force, and then at some point, it comes to the point. Again, you keep lowering, and the rate is going to decrease, right? As you can see here. So on the x-axis you have thermal driving force and the rates, and this blue curve is the Marcos theory, which is the classical approach. Black, which I guess is too difficult to see, it's the exact approach, comes from solving Schrodinger equation, and SC is the semi-classical instanton approach, and GRQTST is our new approach, right? And as you can see, GRQTST consistently accurately predicts quantum rate constant at wide parameter regime. A particularly appealing feature of this approach is that it is able to predict rate constant accurately, even deep in the inverted regime, right? Which is quite difficult without extrapolation. And we can do that without extrapolation. And this was like, I guess, a dimensional system bath model. And for this system, semi-classical approach is also working quite well because it's still a harmonic system, right? And we tested our approach on systems with multiple transition states. So this system has 2 instantons. The reaction can occur either from the bottom channel or top channel. And this is a nice system to study because this is typical of liquid system, right? Liquid system, the potential energy surfaces cross at multiple points, and there are many channels reaction can occur. And here I have plotted configuration space sampled in GRQTST approach, which is this green. This blue and red paths, they are instanton. These are instanton, and it samples region in the vicinity of instanton, right? And this black one is another approach, which people have used to do liquid state reactions, and it is seen to not sample accurately, at least for the system. But the system is still accurate for a lot of other chemical reactions. These are just numbers to show that the approach works well. And this paper from our lab, they also tested our approach on ferrospheric system. I guess it is 1000 dimensional system, and saw that the system behaves as a harmonic system in the classical limit. And we also tested highly quantum mechanical system. So instanton was cooled down to very low temperature. It proves to be quite a challenging system. There's only one instanton in this system, and because it's slightly curved, for some reason it is difficult for other approach to treat it. And we found that for, again, wide range of imaginary time split, it samples region around this transition state, right? This red cross. Yes, and yeah, there are also other applications of rate theory such as this. Like I said, I work as a quantum engineer at IQM Quantum Computers, and we are building quantum computers. At least the hardware team is building quantum computers. And so in quantum computers, tunneling is omnipresent. And so these are like architecture for quantum computer. On the right, you see this is IBM's chip, and it has 2 qubits. Qubit 1 and qubit 2, they are connected by this tunable coupler. You can change the frequencies of these 2 qubits and make them interact by applying this magnetic flux pulse, and there's this resonator, which is basically harmonic oscillator, which you interact with qubit, and this is going to help you to perform the read out the states of qubit, right? And you see this kind of chips, I guess here somewhere. I'm not too much into experiments, right? So a lot of these cables I would not understand, but you should find this chip somewhere there. And that is our lab at and this is IQM's setup, and this is the lab at ATH, quantum device lab, and you need to cool this down to almost 0 Kelvin, right? And then you see quantum phenomena. And these superconducting qubits, they are made out of electrical circuits, and the simplest electrical circuit is LC circuit, and LC circuit is composed of capacitor with some inductor, right? This capacitor stores energy in electric field, and inductor in magnetic field, and you need to cool this down to low temperatures such that current flows dissipation less, right? And at this really extremely low temperature, this big macroscopic thing starts to show quantum phenomena, and you can basically quantize, right, this macroscopic variables into this Q-like and P-like variables, and you can basically make this into a harmonic oscillator, right? And you have this quantized eigenstates. But this is still not enough to make qubits, because all these energy states, they have equal spacing, and the microwave drive that is resonant to this one is also going to be resonant to this one. So you are not in the computational subsystem all the time. But for qubit, you need like really separated 0 and 1. But for transmon, which is what you define qubits with, has this simple inductor, linear inductor replaced by non-linear inductor, and you make this anharmonic potential. And now this anharmonic potential is cosine-like potential, and you have something like this, right? So the well, you can use this well to create metastable states, 0, 1, 2, and 0 and 1 has some spacing, and 1 and 2 has a bit different spacing. And you can compute the tunneling rate to go from, let's say, 0 to this side, right? And from here you can measure the current, I guess, and you can tell if you were in 0 state or 1 state, right? And I used my approach to compute tunneling enhancement for this kind of potential, which is seen in superconducting qubits. And these are rates, and these are like temperature. Because it is bounded from below at extremely low temperature, the rate starts to stay constant, and we get a qualitatively good picture, right? Because this is the exact rate. You can compute the exact rate. I think I received this number from my professor. You can compute it exactly at like beta infinite, which is 0 Kelvin. And we get a quantitatively good picture. This is instanton approach. Here, instanton works well. This other approach is starting to fail and doesn't give qualitatively good picture. And this is the company's design, IQM's design for the QPU. Yes, so to conclude, just to keep some time for questions, so GRQTST, especially, well, QTST, right, quantum transition state theory, especially in the golden rule limit, has the correct classical limit. So this is one very important, how do you say, feature, right? Because if you want to build a ray theory, I mean, it would be good to also have it, right, reduced to classical approach, and a ring polymer gets shorter and shorter, and we see that it is exact at classical or high temperature limit. It's able to treat an harmonic system because it doesn't make any kind of harmonic approximation for quantum fluctuation. There was an integral, right, there, instead of just evaluating your quantum Boltzmann operator at instant configuration. So it is able to account for higher order quantum paths. And GRQTST works in the inverted regime without needing for any kind of extrapolation. the reason why in the inverted regime, I think I should point out that the rate starts to decrease is because you see here, like the path is short, right, to travel. You go here and then here, and you're already there, right? But here in the inverted regime, you have to go here and then all the way down. So there is a longer path to travel, and that's why the rate, I guess, starts to decrease. But GRQC is seen to work in the inverted regime also. And it is able to treat systems with many transition states. For example, this was like ferrospheric system. In liquid water, I guess this was like, I don't know, 1000 diamond system. And we saw that it revealed that this system is like a spin boson model. and these are like references for that where you can read more. And I just want to give acknowledgement to ETH Zurich. ETH Zurich Research Grant, it supported my PhD studies. It's my Professor Jeremy Richardson. It's a postdoc, Wei Fang, and doctoral student currently, Rhiannon. Also, our collaborators at EPFL Lausanne. And yeah, last but not least, I want to thank especially Jacobs University, where I honed a lot of this scientific skills when I was doing my BSc there, right? And thank you all for listening. And I'm open for questions now.
Yeah, thank you very much, Manish, for this very clear and pedagogical presentation. So there is actually one first, no, it's not it's just a comment by Ulrich. Do you have also a question, Ulrich, right now? So if not, then, so I do not see another question in the chat. So yeah, let me just start by asking maybe the first question. So when you are doing the instanton approximation in certain systems, you have to consider geometrical phases. For example, if you have spin-orbit interaction. And so did you encounter situations, or did you consider situations where in your approach you have to include Berry phase, geometric phase?
That's a very good question. I never encounter geometric phases, right, for spin orbital coupling. Yeah, I'm not very familiar with geometric phases, so I guess it's quite difficult to answer that for me. But we did not encounter a situation like that. We did not at least include those situations because we are treating nuclear tunneling, right? So I'm not sure for vibrational states, if that would be relevant.
Yeah, it could be relevant for the application to quantum computation, at least for some systems, because they involve not the kind of superconducting qubit which you presented, but there's a suggestion, for example, to use spins also, and they are certainly geometric phases might be important to include.
Okay, I see.
Yeah, so are there other questions from the audience, from my colleagues, from students?